welcome to the lecture on dimensional analysis. So, we talked about the similarities. Now, what we do normally in the case of dimensional analysis, it is frequently used in the process engineering to represent a physical phenomena in terms of mathematical equation that is essentially dimensionless. So, basically if we have these equations we talked, if you know the equations governing the fluid flow or heat transfer or so. So, in those cases what we do is normally we try to have this equation in the dimensionless form. For example, if you talk about the fluid flow equation. So, what we do normally is you have V. So, we are expressing it by dividing with a characteristic velocity. Similarly, P star will be that is P minus P naught by P V square. So, this way you get you have again T star. So, T star will be T into V by L. So, you have characteristic length, you have a reference velocity. So, similarly x star will be x will be divided by a characteristic length, then you have y star again y by L, or z star will be z by L. Then you get you have the operators point with these they also need to be expressed. So, so that star that will be L times grad. So, that will be again you will be using. So, you will have delta 1 times similarly you will have star square. So, that will be L square and that you will be delta square. So, you will have dou square by dou x star square like that. So, you will have dou square by dou x in this case you will have dou square by dou x square and delta 1 multiplied by that. So, that way you do, and then once you put them into the equation for the continuity and also the momentum conservation. So, in that case also if you you must have done that, and in that case you get the two kind of number dimensionless numbers, and that is one you are getting as Reynolds number, that is LV rho by mu, and then you are also getting the Froude number, that is V square by GL. So, this is how that is used for that is the use of these non-dimensionalizing, and then on both these sides when you do. So, you get you will be having the expression coming up like d V star by dt. So, and dt star. So, that will be coming as minus of grad star P star. So, that is what you do normally. You have the first term dou p by dou x or so, and then you get the term like mu by L V rho, and that multiplied by grad star V square V star, and then you get GL by V square, and then you get that is multiplied by G. So, G star is coming. So, basically what you see, you are getting these two terms. So, so that is what it is coming. You get these non-dimensional quantities, that is what you are getting. What I mean to say that normally we try to convert these equations, that is essentially dimensionless. Now, this technique which is generally applied, it is to work out a relationship between the various measurable quantities in a system. So, what we there that if you talk about any system, so you will have one variable that will be represented in terms of other parameters or other variables. So, you will have to have a particular relationship, and you determine the minimum possible number of variables required to define the geometry and also operating conditions in the system, and then you go for scaling down or scaling up of the system. So, that is the the way you that there is the technique which is normally applied. So, the first method which is used for such approach is the Rayleigh's method of indices. Now, what Rayleigh's method of indices say that in this case the dimensional analysis will be based on the method of indices. So, what happens that the relationship between different physical quantities can be expressed as the product of power functions. So, what you do here that you have x naught, suppose this is a dependent variable, and that is expressed in terms of C1 into x 1 raised to the power a, x 2 raised to the power b, and similarly x 3 raised to the power c, and so on. So, suppose C1 is expressed C1, a, b, and c, all these are the constants. So, if you try to have the dimensionless groups. So, if you see further, if you have the from this place onwards, again you can have the capital X1, capital X2, and a capital X3. So, they can even be expressed, you can have these dimensionless groups defined, that is capital X naught, similarly capital X1, capital X2, and a capital X3. So, they also can have with the different constants capital A, B, C, you can express them. So, you can further express, like if you have non-dimensional group. So, that is x naught can be expressed as the C1 prime, and you have the x 1 raised to the power a, and similarly x 2 raised to the power b, similarly x 3 raised to the power c. So, these are the non-dimensional groups that can also be expressed in terms of these indices, and that will be going on. So, here again C1 prime, then a, b, and c, they are again the constants. So, and then you are we will see that they will be further equated on both these sides, and you can have the evaluation of these constants, and you can see that how they can be expressed. Another method which is also used is the Buckingham pi theorem. So, now in this case it is normally used in the dimensional analysis to determine the number of dimensionless groups that one can expect in the analysis of any given physical phenomena. So, here what you do is normally you are having the number of the dimensionless groups you are trying to determine, and that will be depending upon the value that will be equivalent to the E minus f. So, you have basically f that will be representing the total number of primary quantities which is required for the expressing, and then the E value will be representing the total number of independent and dependent variables which will be governing the process. So, E minus f will be basically telling you the number of those pi groups, and then this way you can have those dimensionless numbers coming into existence. So, that can be found out. So, what you do in this case, you have f of pi 1, pi 2, pi 3, that will be. So, in the case of pi theorem, you will have the pi 1, pi 2, and pi 3. So, they will be equal to 0. So, they will be basically they are the independent products of the arguments that is there, which is dimensionless, and you find these now how many numbers will be there, that will be equal to E minus f. So, this way you try to have the calculation of these pi groups. So, for example, if you look at one of the problem, like you have to have the rising velocity you have to have this for this problem rising velocity of spherical shaped particle, spherical shaped inclusion in a stationary fluid. So, suppose you have to have the calculation of the dimensionless these groups. So, what you do, you can have the use of this Buckingham PI theorem, and what we see that normally if you talk about the rising velocity which is there, because this is a problem in the case of steel making, where the inclusion, if they are normally lighter and they have the tendency to float towards the upper side. So, normally your V rise, so this V rise will be a function of the weight of the particle, then you have the density of the particle, you have the coefficient of viscosity of the medium, and also the density of the medium. So, normally it is a function of weight of the particle Wp, you have diameter of the particle, you have the coefficient of viscosity of the medium, and the density of the medium. Now, if you use these Rayleigh's method of indices, so you can write a functional relationship of the type. So, you will have V rise, it will be C1 times W rho. So, that will be power A, then dP raised to the power B, then you have mu raised to the power C, and then similarly rho raised to the power D. So, that way you can have you can these are the indices which are these. So, you will have the to know the what are the dimension of these variables. Suppose your variable is your rise velocity. So, you are symbol is you have Vr, and its unit is, as it is a velocity. So, it will be meter per second, and if you have the to know the dimension, so it will be Lt minus 1. Similarly, you have the weight of the particle, and weight of the particle you do it by Wp. So, it will be normally kg meter per second square, and you will have ml t minus 2. Then you have the density. So, if you talk about the density of fluid, so you have that is rho. So, you will have kg per meter cube, and it will be ml minus 3. So, then comes your after density, you have the diameter of the particle. So, you have dP. So, diameter will be in terms of meter only. So, so you will have m. I know this is L, and then the last is your mu. So, that is coefficient of viscosity, and that is mu, and that will be kg that is if you look at, that will be kg per meter per second, and you will have ml minus 1 t minus 1. So, once you know, you must have the idea about these dimensions, and you have to equate on this side. You have to find the number of pi which is required in that case. Now, in this case, if you look at the number of primary quantity is 3. So, number of primary quantity will be 3, and if you look at the independent and dependent variable, that is Wp, dP, mu, rho, and V. So, that is your 5. So, E is 5 and F is 3. So, in that case, if you go for E minus F will be 2. So, you will have two independent pi groups that you can form. So, you will have 2 independent pi groups, and that will be required for the representation that is in the dimensionless form. So, you can write that f prime pi 1 pi 2 that will be equal to 0. Now, what you see is that if you equate on both these sides, so you have to have the dimensions on both these sides. So, you have in the earlier case this is L t minus 1. So, you will have m 0 L and t minus 1. So, that is and that will be that we have seen that you will have the 4 parameters and that on that have the indices a, b, c and d. So, so those values are W p on that a, d p, b and mu and c and rho on d. So, you will have those expressions. So, you will have m l t minus 2 that will be a. Similarly, you will have L that is on b. Similarly, you will have ml minus 1. So, you will have those values. So, you will have then mu will be ml minus 1 and t minus 1. So, on that so we have taken rho raised to the power d. So, rho is your ml minus 3. So, you will have ml minus 3 and you will have the ml minus 1 t minus 1. So, ml minus 1 ml minus 3. So, kg per meter cube and then you will have ml minus 1 t minus 1 and that raised to c and d. So, basically you can have you can do the equation can be equated. So, this side it is 1 and if you look at here it will be 1. So, that is a plus b and then you have minus 3c and you have minus d. So, that will be 1. So, 1 will be a plus b minus 3c minus d. So, similarly you have t is m is 0. So, 0 will be equal to if you look at the m. So, it will be a, then you have plus c and here also plus d. So, this way and if you go for t. So, it will be t is minus 1 on this side and on this side if you look at it will be t is here it is minus 2a and similarly you will have t as minus d. So, ml so that way you will have the equations. So, that you can come and if you equate these equations. So, you will have that is minus 2a and you will have further minus d. So, you can have you can find these a, b, c and have d. So, if you manipulate these equations then you can have you can find the value of b as minus 1 and that you can have the expression of c and d are expressed in terms of a because you have 3 equations and 4 unknowns. So, c and d can be expressed in terms of a. So, you have c as a minus 1 and d as 2a plus 1. So, we can have that minus 1 as minus 2a minus d. So, you get b as minus 1 that by some manipulation and then you get the c and d expressed in terms of a. And you can have further you can express the in terms of the 2 quantities that will be f of rho v rise dp upon mu and w p rho by mu square. So, that will be equal to 0. So, basically you are in a position to devise 2 kind of non-dimensional numbers, that is for these inclusions when you do the inclusion analysis, and the 2 groups which you get will be that will be rho v rise dp upon mu and the another group which you get pi 2, it will be W p then into rho and divided by mu square. So, what you see now, if you look at these numbers, what you see, this is nothing but this is the number which is analogous to the Reynolds number which we have studied, rho v d upon mu. So, and this is another dimensionless group which you are having in that case. So, this way you try to have the solution of these equations. So, you have to first write down these two equations on both the sides. You have to have the indices being equated, you have to solve, and then you get these expressions, and further you are having these values of these two pi groups. So, so that is how you get these non-dimensional numbers, and they have their significance. So, when you are trying to analyze that system, that time you try to have the use of these numbers. So, you may have different types of dimensionless groups which are used in the case of Tandis modeling, and like when you go for the fluid flow type of cases. So, in the case of fluid flow, you have the group is your Reynolds number, and that is by rho L u upon mu. So, that is how you have these dimensionless number group, that is. So, this is your application, and that is how you define. So, this is your definition, and this is the group. Similarly, if you go for the wave and surface behavior, so in that case what you do, or when you are going to use for the pouring stream. So, in that case you have that value is u square by GL, and that is your Froude number. So, we have seen this number, we have talked about, we have dealt with this number earlier. So, that is your the Froude number. Similarly, you go for the forced convection or mass transfer. So, in those cases you have a number that is your Peclet number, and the Peclet number will be Lu upon alpha or Lu upon d. So, that way it is basically the ratio between convection and diffusion. So, that way you get these Peclet number defined. Similarly, when you have the atomization of liquid jets, in those cases you come across the number that is your Weber number. So, there you have the surface tension term coming into picture. Then many times in the case of forced and free convection, you come across the group, and that is your Prandtl number, and the Prandtl number is defined as mu Cp by K. And in the case of mass transfer, when you will deal with the concentration equation, or when we will be solving for the scalar transport equations, in those cases you have a Smith number. So, that is a Smith number, and that is the group is mu by rho d. So, that is that is also used. So, normally you have a certain value assigned to it, we assume. So, basically these are the different type of groups which you normally come across. So, you will also come across other numbers like you come to for the Tandis-Richardson number when we talk about the convection or natural convection, especially when we deal with the heat transfer cases. So, in those cases those numbers also are coming into picture, and these are the groups. So, that is you are they are going to be dealt with when we deal with these cases. Then there that is normally used. Now, these values also it has been reported that when you use these various dimensionless numbers or groups. So, normally you go for the water modeling in the case of the Tandis system. So, the steel is basically replaced with water because their kinematic viscosity is same at the melting temperature of steel and at the normal temperature in case of water. So, normally you have when you go for the full scale model. So, when you have this, so if you talk about these numbers and you have the steel system. So, and if you go for the full scale water model. So, if you see that when you talk about these Reynolds number, so you do the Reynolds similarity. So, in that case if it is 1, so normally it is reported in the by Le-Boussier and Jackley that normally we should report it to be 1.1 for the Reynolds number. In steel system it is 1, so full scale water model you can have 1.1. Similarly, you can have for the Froude number. So, if it is 1, so you here also you keep 1. So, that Froude Froude similarity is normally kept in mind. So, that is in the steel system it is 1, then full scale water model also you keep it as 1. So, similarly for the Weber number, if you talk for Weber it is if it is 1, so in that case it is will be 3.1. So, similar to that you have other numbers like you have sometimes the Morton number. So, Morton number is the one which is used for the velocity of bubbles in the liquids, and that is normally used for the two phase flows or multi-phase flows when we do in the Tandis. So, in those cases for the this is the dimensionless group is the Morton number, and that is G mu so you have an expression for that, and for that for the full scale water model that ratio becomes close to if it is 1 in steel system it is coming close to 45 in the water model. So, these these numbers, so that needs to be kept in mind when you are doing the water modeling, and how that full scale water model, how these numbers, how these for the steel as well as full scale model, what numbers should be there. So, that you need to know. So, that can be taken as a reference from the literature also, and this is how typically they vary. So, this is about the dimensionless doing the dimensional analysis in the case of this Tandis system, and we will when we will be doing that discussing about these water modeling or the scaling. So, at that time we will have the introduction to these numbers, especially the Reynolds and the Froude. So, you will have the similarity based on these two, that is what we have already discussed, and also their significance in those cases. Thank you very much.